In today's activity, we learn how atoms can bond together to form either molecules or compounds. By the end of today's lesson, you should be able to explain the different types of bonds that atoms can make. When you eat a meal, it's like filling your car's tank with gas. You have a source of energy that can then be used to fuel activities like running, thinking, building muscle, and maintaining that machinery of life. That energy initially comes from the sun and is captured and stored by plants. And when we then eat the plants or eat other animals that have eaten the plants, we ingest the energy stored in the plant material. But how exactly is energy stored in plants? Groups of atoms that are held together by bonds are called molecules, your first vocabulary word of the day. And it takes a certain amount of energy to break a bond between those two atoms. The amount of this energy, which is called the bond energy, vocabulary term number 2, depends on the atoms involved. When chemical reactions occur, such as when animals or even humans consume and digest molecules in their diet, some existing bonds are usually broken and some new bonds are usually formed. If the bond energy of the new bonds formed is less than the bond energy of the starting materials, the excess energy gets released and can be used to fuel the body's activities. In a sense, molecules are created as a short-term storage of energy that can be harnessed later. Before we go any further, let's stop for a moment and take a look at how molecules tend to be illustrated. Throughout this course, we'll see molecular structures represented mostly by ball and stick figures or models, as well as space-filling models. But there really are 3 different ways that we can represent molecular structure. There's the Lewis model, which you see is the first item, which shows the symbol of the element and whether or not there's a single or a double bond. The ball and stick model would use circles around each of the symbols for each of the different elements in that molecule, and they represent kind of the relative size. So what you see here is hydrogens bonded to a central carbon, and you see that the carbon is actually a larger circle than the hydrogens. So it gives you the sense that hydrogen is a smaller molecule than that carbon. We also use what's called the space-filling model. It's an attempt to try to give it a little bit more of a 3-dimensional feel, even though it's still really 2-dimensional, but it looks a little bit 3D-ish. So it gives you a better sense of the space in which these molecules fill, and also kind of their shape. All right, so let's take a look at the bonds. There really are 3 principal types of bonds that hold atoms together. And the type of bonding that any atom is likely to take part in depends almost entirely on the number of electrons in its outermost shell. Covalent bonds is the first type of bond we'll look at. When 2 atoms share electrons, a strong covalent bond is formed. And the simplest example of a covalent bond is the bonding between 2 hydrogen atoms to form a hydrogen molecule. This is represented as H2, H with a subscript 2. And this really is the simplest of all molecules. The hydrogen atom has an atomic number of 1, which means, as you know, it has a single proton in its nucleus and a single electron circling around the nucleus in that first energy shell. And because the atom is most stable when the first shell has 2 electrons, then 2 hydrogen atoms can each achieve a complete outermost shell by sharing electrons. The nuclei come close together, but not too close because they're positively charged and their mutual repulsion would really destabilize the molecule. And the 2 electrons circle around both of those nuclei. So it's almost like they're moving in a figure 8. So the new H2 molecule is very stable because now both atoms have 2 electrons in their outermost shell, and therefore they're no longer likely to bond with any other atoms. The sharing of two electrons between two atoms forms what we call a single covalent bond. Take a look at the oxygen atoms in this image. Oxygen has an atomic number of 8. So that means it has 2 electrons in its innermost shell, closest to the nucleus, and then it has 6 electrons in its second shell, or its outermost shell in this case. As a result, it needs to gain 2 more electrons to fill its outermost shell because it wants to have 8 electrons, which is the maximum amount of electrons that can be held in a second energy shell in order to become very, very stable. This is called the octet rule, the rule of 8. Each oxygen atom in this illustration will then share a pair of electrons with each other. And that means that each one gets to claim that they have, in a sense, they get to claim that they have a completely filled outermost shell. So the sharing of 2 pairs of electrons between 2 atoms is called a double bond, another one of your vocabulary words. O2 is the most common form in which we find oxygen in the world. In fact, oxygen gas, which we breathe, is all O2. Let's take a look at carbon. Yeah, you might call carbon an extroverted atom. It has an atomic number of 6, so if we add that up through the shells, that means that 2 electrons fill its first shell, the total max for the first shell, leaving 4 remaining electrons to occupy the second shell. And because basically that leaves us with 4 electron vacancies, that means carbon, and it frequently does this, it means that carbon can form 4 additional covalent bonds. And so it can join up with other atoms in a large variety of different types of molecules. Methane, for example, is the chief component of natural gas, and it's formed when 1 atom of carbon covalently bonds with 4 atoms of hydrogen. See that here in this illustration. So that's covalent bonds, the first of the 3 bonds that we're looking at in this lesson. Our second type of bond is called ionic bonds. So atoms can also bond together without sharing their electrons like they do in the covalent bonds. So when one atom transfers 1 or more of its electrons completely over to another atom, then each atom becomes an ion because each atom then has an unequal number of protons and electrons. The atom gaining electrons becomes a little more negatively charged, while the atom that's losing electrons becomes a little bit more positively charged because it has less negatively charged electrons. An ionic bond occurs when the 2 oppositely charged ions attract each other. And unlike covalent bonds, when we have ionic bonds, each electron circles around just a single nucleus, not both of them. Ions of 2 or more elements linked by ionic bonds form what we call an ionic compound. Because the ions are attracted to each other, and because they're of equal and opposite charge, the compound is then neutral. That is, it has no charge. A common ionic compound that you might be familiar with, well, you definitely are familiar with, is what we call table salt. It's really NaCl, sodium and chloride. And the sodium and the chloride that it's composed of are ions. And now for our third type of bond, and that is the hydrogen bond. Ionic and covalent bonds link 2 or more atoms together within an ionic compound or a molecule. Hydrogen bonds, on the other hand, are important in bonding molecules together. A hydrogen bond is formed between a hydrogen atom in one molecule and another atom, often an oxygen or a nitrogen atom, in another molecule, or even in another part of the same molecule. This bond is based on the attraction between positive and negative charges. Atoms taking part in hydrogen bonds are not necessarily ions, so where do the electrical charges come from? Well, the hydrogen atom is already covalently bonded to another atom in the same molecule, and it is sharing its electron. That electron circles both the hydrogen nucleus and the nucleus of the other atom, but the electron isn't shared equally. It's as if the nuclei of the atoms are playing kind of a tug of war with the electrons. Because the other atom always has more than one proton found in the hydrogen nucleus, it's more positively charged. As a result, the electron contributed by hydrogen spends more of its time near the other more positively charged nucleus than near the hydrogen nucleus. Having an extra electron nearby causes the larger atom to be slightly negatively charged, while the hydrogen atom becomes slightly positively charged. In a sense, molecules with slightly charged atoms become like a magnet with distinct positive and negative sides. And they're also said to be polar in that case. Polar molecules are attracted to other polar molecules, lining up in particular orientations so that the positive regions of one molecule are near the negative regions of the other. A hydrogen atom with a slightly positive charge can become attracted to an atom in the neighboring molecule with a slightly negative charge. These attractions are called hydrogen bonds. Although hydrogen bonds are only about 1/30th as strong as covalent or ionic bonds, a multitude of hydrogen bonds form in water and are responsible for many of the unique characteristics that make water one of the most important molecules for life on Earth.